Okay, everybody, this is me once again, and this time I want us to deal with the problems. But before we can go into these problems, I believe it is very important that we have some reading to do first. So, power functions. A function f at x is equals to x to the exponent of n. So, the base and the exponent constitute what we call a power. So, let me just zoom in. Okay. And let me just do this. Let's just wait for it. There it is. So a function f at x equals a x to the exponent of a, where a is a constant, is called a power function, and there are several important cases to consider. So these cases are very important. So when a is equals to n, where a is a positive integer, the graphs of f at x equals x to the exponent of n for n equals these natural numbers 1, 2, 3 and so on, which are displayed in figure 1.15. These functions are defined for all real values of x. So for negative, positive, fractions, rational, irrational, they are defined because they are defined for all real values of x. Notice that the power n gets larger. Notice that as the power of n gets larger, the curve tends to flatten towards the x-axis on the interval -1 is to 1, and to rise more steeply for the modulus of x is bigger than 1. So when x, remember here, x will be greater than 1 and minus x will also be greater than 1, because we know that the modulus of x is equals to x for x is greater than 0 and minus x for x is less than 0. So each curve passes through the point 1 and 1 and through the origin. Okay, that is fine. The graphs of the functions with even powers are symmetric about the y-axis. We've already looked at that. Those with odd powers are symmetric about the origin. Okay, the even powered functions are decreasing on the interval -infinity is to 0. We can see that the even powered functions are decreasing on the interval -infinity is to 0. So from -infinity is to 0, the curve is decreasing, and from 0 to positive infinity it is increasing. So this happens for the even powers of x, and we can see that from -infinity to 0 it is decreasing, and 0 to positive infinity it is increasing. Okay, so that is fine, and increasing on the interval 0 is to positive infinity. The odd powered functions are increasing over the entire real line from -infinity to positive infinity. Is it true? Yes, it's true for this one. It's an odd function. It's true for this one. It's an odd function. It's true also for that one. It's an odd function. So these are the domains. Very, very important that we see this. For even powers of x, we have this domain. The graph tends to flatten towards x-axis on this interval. Remember, these are the values of x. So these are the domains, and then each curve passes through the point 1 and 1 and through the origin. Okay, that is fine. So they say the even powered functions are decreasing on that interval and increasing on that interval. The odd powered functions are increasing over the entire real line. Okay, before we can go any further and look at many other things, let's just go and investigate these functions. So what I'm going to do, I'm just going to come somewhere here. There it is. And what we want to do there is to draw these functions and investigate some few things. So let me just say close. I'm gonna come here and say insert a function. So the very first function is this one that I'm going to insert. Y is equals to x. So f at x equals x. Remember, this is y. So y is equals to x. And I'm just going to leave it like this, and I'm going to choose a different color. Let's use a color such as, let me check. Let's take this one. Let's take this one. And let me just press OK. And we have this function f at x equals x. There it is, exactly the same way as we have it there. Right. And we can investigate the domain in here. We can see that because it's an odd function, they said now the odd powered functions are increasing over the entire real line. From negative infinity is to positive infinity. And I can see from negative infinity to positive infinity, it is increasing. As you can see, we are moving from negative infinity to positive infinity, and it is increasing. So as the values of x increases, so are the values of y. We can see that. So it is an increasing function. Okay, that's fine. I can just come here, f at x equals x, which is y equals to x in other words, and the argument range, I can say, okay, let's start from 0 to 3. Okay, and let's just see whether there will be any changes that transpires. Yes, there are. So what are we saying there? We are just saying our interval, start drawing our graph from 0 until to the point of 3. I can change here and I can say from -3 to 3, and I can press OK, and I can have this. But if you do not specify the interval, here, it will start from negative infinity is to positive infinity, and you will have it in this way. It's very, very important that we try to understand that. So this was just for the first one, trying to understand it's an odd function, and the odd function increases from negative infinity moving to positive infinity. So I'm going to draw another one, and this one, it's y equals x squared. So I'm going to draw on the same axis, so x, and then what you do there, you just press shift on your laptop and you press this arrow, and then you press your 2. This is x squared. And let me just draw this with a different color, and I'm going to use this one. Right, and I'm not also specifying the interval here. Let's check what is happening. But in here, let me just specify some things. Start, I want it to start with this red, and I want it to end with this, and I'm not specifying the argument range there. And then I just press OK. Let me just do this. Okay, that's fine, and we have it in this way. The graph of y is equals to x squared. It's a parabola. Here it is, and as you can see from there, I did not specify the interval. So I can say to this, start from 0 and end at 4. I can do this just to show this portion on the side, and I can press OK, and I can have my function in that way. But that's not what I want to do. I just want it to start from negative infinity is to positive infinity. and then I have it in this way. So I'm just trying to show you how these functions works. And for every value of x, you have exactly one value of y. So it passes what we call the vertical line test, and we can see this, that it is a function, because for every one value of x, you only get one value of y. Okay, let's continue and let's try to draw that one. So we can just come here, function, insert a function, and this is x to the exponent of 3. And I'm also not specifying the interval, but I want to use a different color, and I want to say start from this and end with that, and I want to press my OK. And there is the function that we have. Let me just try to change things a little bit. The color seems to be a little bit dim, so let's just try to use this one. Very good. So there we are, we have this function. So remember what we said. We said it should start with that and end with that. So this is from negative moving like that towards the positive. And remember here what you have done. Remember what you have done here. If you did not specify the argument range, it will by default move negative infinity is to positive infinity, and we have that. Okay, and then we can go for this one. I can just come here and I can say a function. I can have x to the exponent of 4, and I can use, I believe, a black color, and I can just say start with this and end with that, no problem. And there it is. There it is. Let's see whether is it the same. Yes, it is the same. There it is. And remember what we have read with these functions. Remember, it's an even function. So they say the graphs of the functions with even powers are symmetric about the y-axis. So that is no coincidence, we can see that. Okay. Those with odd powers are symmetric about the origin. That is fine. This is not what I'm looking for. They say notice that the powers of, as the powers of n gets larger and larger, remember for even functions, as the powers of x gets larger and larger, the curves tends to flatten towards the x-axis on the interval -1:1. There it is. It flattens on the interval -1:1. We can see this. Okay, let us try to look just to make some sense. Let me just come here. I want to demonstrate something for you. Let's take x to the exponent of 6, and using the very same color, which is black. And do you see what is happening now? Look at this one, this one. Look at this one. It will always and always flatten on the interval of -1:1. No matter how big you can try to make these numbers, it will always and always. You see what is happening? Always and always. So I can come here and I can make this to be a value of 10, and it will always wrap itself around, flatten around the interval -1:1. This is just something worthy of noting, because it justifies this. Tends to flatten towards the x-axis on the interval -1:1, and to rise more steeply for the modulus of x, which is bigger than 1. So it is very important that we note these graphs. So okay, that is one. So graphs of f at x equals x to the exponent of n for n equals 1 2 3 4 5 and so on, defined on the interval negative infinity is to positive infinity. So when a is -1 and a is -2, let's see what is happening. The graphs of the function f at x equals x minus 1, which is equals to 1 divided by x, and g at x equals x minus 2, which is equals to 1 divided by x squared, are shown in the figures. They are shown in here. Okay, that is fine. Let me just come here. I just want to come here and delete, and I also want to delete, and I also want to delete this one, and also delete that one. And I don't know why we are still having you as well. Right, so let's have these functions just as we have them in there. Y equals 1 over x. So let's just say 1 over x, and let us just draw this. Start with that and end with that. And here we have this function. We know what this is. This is a hyperbola. If the value of a is positive, it will be on the first quadrant and on the third quadrant. Let me draw the second one. So we have 1 divided by x to the exponent of 2, and we have it like that. Let me just use a different color. Let me just use a color that is different. Let me check this one. Yes, there it is. Okay, so we have these functions also in our graphical way of representation. And what is happening here? So they are drawn in the domain. X cannot be equals to 0 because we can see that we have an asymptote there. Here x cannot be 0, we have an asymptote, and y cannot be 0 because this is the vertical asymptote, the horizontal asymptote. It's a line that the graph will approach but never touch. Also the line that it will approach but never touch, no matter what you can do. The same is happening here. The domain x cannot be equals to 0. We can see that range y should be greater than 0. The values of y should be positive. Only positive y values. There they are. From here moving upwards, we cannot accept values that are negative. Okay, that is fine. We understand why this is so. So the graphs of the power functions f at x equals x to the exponent of a. For part a equals -1, and for part b, a equals -2. So when a can be half, 1/3, 2.5, 2/3, and so on. The functions f at x equals x to the exponent of 1.5 equals the square root of x, and g at x equals that, which is this when you rewrite this. So x to the exponent of 1/2 is the same as the square root of x. We know this, and this is the same as that. We know that when we dealt with rational exponents, the square root and the cube root functions respectively. So this is the square root and the cube root functions that we are having. The domain of the square root function is 0 is to positive infinity. Let's check that. Let me just come here. Y equals the square root of x. Let's just investigate that. So let me just do this. Let me just delete these ones, delete that one. So let's have a function y equals the square root of x, which I can write as x to the exponent of, and I'm going to have a bracket, 1/2 is the same as 0.5. And let me use a black color and let's draw that. And let me just move our graph a little bit to the side. Okay, here we have it. And remember what they are saying here. They are saying the domain of the square root function is 0 is to positive infinity. And look here, we have a closed interval here. So the function is defined at x equals to 0. And let's check. Yes, x equals to 0 moving to positive infinity is the domain. So this is correct, what they are saying there. But the cube root function is defined for all real values of x. Let us go and investigate that. So I'm going to draw another function here, which is y equals x to the exponent of 1 divided by 3, because this is exactly what we were told there. So let's just draw this one with this color, and let's just have the beginning and the end. And look what we have now. Let me just move it to the side. You see what is happening? And they are saying where is it now? The domain of the square root is that, but the cube root function is defined for all real x, and we can see that it is defined on the entire real number line. So when we want to find the domain, it's from negative infinity is to positive infinity. It is defined in every domain, in every real number system, as we can see that for all real values of x. So from negative infinity is to positive infinity. Right, okay, that is fine. We have understood and drawn that, and then we will look at polynomials. And they say a function p is a polynomial if p at x equals a to a n xn plus this. Okay, that is fine, where n is a non-negative integer and the numbers a0, a1, a2, an are real constants called the coefficients of the polynomial, and all polynomials have the domain negative infinities to positive infinity. All right, okay, that is fine. Let's continue to read. If leading coefficients a n is not equals to 0 and n is bigger than 0, then n is called a degree of the polynomial. And then they say linear functions with the gradient that is not equals to 0 are polynomials of degree 1. Okay, polynomials of degree 2, usually written as this, are called quadratic, likewise cubic functions, and so on. We know that. I'm not going to draw these graphs. We already dealt with that one. We dealt with this one. You understand that one. This one is also very simple. So you can see that the domain is very clear in this one, even the range. And the range, you can see that y should be greater or equals to 0, positive y values, and y should be less than infinity. So the values of y, the range, this is not heading towards negative infinity in terms of the range, but we are saying y should be greater or equals to 0. This is good, and y should be less than infinity. The same with the domain. X should be greater or equals to 0, positive x values, and x should be less than infinity. Very important that we try to understand these things. This is so important that we try to understand that. So these are the domains and the ranges. So x should be less than infinity and y should be less than infinity. So we are therefore saying as the function is moving, the function will not keep on going up towards infinity. No, it should be less than infinity. Very important, the domain and the range of this function. The same transpires here. The values of x that are bigger than negative infinity, which values are that? Values that are bigger than negative infinity are the values moving this side, and values that are less than infinity are the values moving to that side. So that would be the domain of this function. X should be greater than negative infinity, move to this side. X should be less than infinity, move to that side. And then the range, y should be greater than negative infinity, move this. Y should be less than infinity, move that. Very important that we see that, right? And then we come to this one, and we can see this is pretty much straightforward. The domain, x should be greater or equals to 0, positive x values, but x should be less than infinity. And then the range is that way. And then we look at this one, x should be greater than negative infinity, there it is, and x should be less than infinity, there it is. And then we have the range, y should be greater or equals to 0, and y should be less than infinity. We need to take note of these things. And then we have these polynomials, as many as they are, and we have them like that. And then we also have a rational function, and they say a rational function is a quotient or a ratio f at x equals p at x divided by q at x, and both are functions where p and q are polynomials. They can be of degree 1, 2, 3, 4, 5, and so on. The domain of a rational function is the set of all real x for which the denominator function should not be equals to 0. The graphs of several rational functions are shown up here. Let us try to see whether we can represent them here graphically as we have them there. Yes, so let me just do this, and what I'm going to do is to take this, copy this, and paste that. So we have 2x, let me check, 2x squared. So let me just have a squared there. 2x squared, sorry, 2x squared minus 3. So let me just do this. Let me insert this inside of the brackets, because I'm going to use the division line here. There it is. And what I'm going to do is to take this one. Okay, let me just say 7x plus 4. So let me just say 7x plus 4. And not to confuse things, let me just do this. Let me just do that. So we have in here f at x is equals to 2x squared minus 3 divided by 7x plus 4. And we try to draw that function. And let's see whether it will be the same as the one that we are having here. And let's see if it is like that. And it is exactly like that, as you can see. we are having the same exact replica. So let me just try to move this one here, try to move this one here. Let's check. This is exactly what we have. We have exactly the same function. So we have been successful in drawing this function. So what is happening there? A rational function is a quotient or a ratio of that, where p and what is that. Okay, that is fine. And then there are a few things that we want to learn from that. Graphs of three rational functions. The straight rate, okay, no, not interested in that. This is just a polynomial. It's a rational function. What is it that we need to learn from this? And then from there they move to algebraic functions and so on. So I'm not very much interested in this. So they do not mention the domain nor the ranges of this, just that the denominator doesn't have to be equals to 0. And then that's that. No domain, no range. And then they speak about trigonometric functions. And then they come and talk about the exponential functions. Functions of the form f at x equals ax, where the base a is greater than 0. So a has to be greater than 0, 1, 2, 3, and so on, is a positive constant. Okay, let's say where the base a is greater than 0 is a positive constant and a is not equals to 1, are called exponential functions. So a has to be a positive value constant and it has to be bigger than 1. It cannot be equals to 1. It has to be equals to something, not 1. Maybe minus 1, maybe 2, 3, and so on. All exponential functions have the domain negative infinity is to positive infinity. Let's try to investigate that. So I'm going to delete this one and I'm going to draw a function f at x equals, let me just say 2 to the exponent of x. Suppose I have this and I draw my graph and look at what I have. This is what I have. Let me just try to use a different color, such as a red color would be fine, I believe. Oh, there it is. So they say they have the domain negative infinity is to positive infinity, and there it is, negative infinity is to positive infinity. Right, I can specify the arguments here. I can say, for example, minus 3 is to 3, and I can draw that, you see. So what we are saying is, as you increase from maybe negative 100 to positive 200, look what is happening, you see. So this is to say it is moving, the domain is from negative infinity is to positive infinity, because you can use infinity numbers. So if we don't want to do that, we know that we can do the following. We can, if we don't want to do this, we can just leave this as blank, and that is just to tell us that we want to draw this from negative infinities to positive infinity, and it will do that for you. So this is the domain of this exponential function, and you can play around with all these and you will find whatever that needs to be established. And then we have logarithmic functions. These are functions of the form f at x equals log ax, where the base a is not equals to 1 and it is a positive constant. They are the inverse functions of the exponential functions, and we define these functions in this section. Okay, that is fine, and we want to go and investigate that. Let's investigate if they are truly the inverses of this. So meaning this will be log 2 base x. So let me just draw that one very fast. So the graph of log, I don't know how I will specify that, log 2x. Let me just check whether it will do what I want. We are having a problem here, because what I wanted to do here, I don't think it will allow me to do that. Okay, let me just leave it. It will not. So but we just have to know that they are the inverse of exponential function, and then that is fine. And then we have the transcendental functions, which I'm not so much interested on. So guys, in our next tutorial we are going to solve these problems. I'm not going to solve all of them, but I will try to solve as many as possible. We are going to try and solve the entire problems that we are having here, and then when we are done with that, we will move on to 1.2. Let me just do this, which is combining functions, shifting and scaling the graphs.